Next up we have moments, and this is actually one of my favourite little topics because it's quite nice. We get to do a lot of fairly simple calculations, and it's just about thinking about what's going on really. It's just quite a nice topic really. Before we go into moments though, we're very quickly going to talk about centre of gravity, because we need to have an idea of centre of gravity before we can start calculating anything to do with moments. So you do need to know the definition of the centre of gravity. So the centre of gravity of a body is the point through which a single force on the body has no turning effect. So basically, if I apply a single force at the centre of gravity, it shouldn't cause the object to turn. Another definition for centre of gravity that you could use is it's the point in an object where the weight is considered to act. So rather than thinking about the weight being divided up all the way through the object, we could say it's going to act just at this one point. And if we calculate based on that, we can figure out, if something's going to topple over or not. So yeah, centre of mass is the place through which all the weight of a body can be considered to act. So a way of thinking about this is the thing about the single force and it not toppling is if you think about if you've got a sheet of paper, if you just apply a force, in fact I've got a ruler here, so if I just apply a force, a single force just here at this one end, oops, put it in the right place, if I let go of my left hand it's going to fall. If I can apply a single force right in the middle, where the centre of gravity is, it doesn't turn, see, it balances. But if I shift my finger to the side, that single force isn't enough to keep it from not turning. So the centre of gravity must be directly above my finger. Okay? So there are a couple of methods that we can use to find the centre of gravity of an object, and the one that you need to know about is this one here. So basically, if you've got a piece of card, what you do is you hang it from a point, and from that same point you hang a plumb bob, which is just a string with a piece of weight on the bottom. It's called a plumb bob because it used to be a piece of lead that was put on the bottom. Those of you who are chemists should know that the chemical symbol for lead is Pb, which stands for plumb bum, which comes from the Latin, that's why it's a plumb bob, or a plumb line. So you hang it like this from the same point that your card is hanging from, and you draw a line. You then hang your piece of card from another point and draw another line. Where those lines cross, so right here on this one, that is your centre of gravity. So this is the method that we use to find it. We will do this in class. You can also find that a centre of mass or a centre of gravity can be outside of the body. So when we do this in class, I want to see if you can come up with a shape where that is true. So centre of gravity is very useful. If you just have a look at the picture here, you can see someone doing the Frosby flop, which was revolutionary at the time because it was a whole new way of jumping over the bar, and you can go over much higher bars because it's your centre of gravity is much lower as you go round, so it's just much easier to keep it going. So if you imagine someone who is just sort of jumping, just scissoring their legs, their centre of gravity would end up being up here, so they'd have to get the centre of gravity much higher, which requires much more energy and it's a lot more difficult. Whereas with your Frosby flop, all you need to do is just skim your centre of gravity straight over the bar, and it's much easier to get over. Okay, right, so that is centre of gravity, which we do need to consider when we calculate the moment of a force. So the moment of a force can also be referred to as the turning effect of a force. It's all about how applying a force at a certain distance can cause a turning effect. So the full definition of a moment is as follows. A moment is equal to the size of the force multiplied by the perpendicular distance from the turning point to the line of action of the force. You're just going to have to learn that, and it's got a lot of important things in it. The most important bits to pull out is perpendicular distance, so it does have to be a perpendicular distance, not just any old distance, and it's the line of action of the force, not where the force is applied. So if we look at just the picture here, I'd say that the force is applied here, the line of action of the force is along here. Now in this case, the distance from the turning point, which is here, to the line of action of force, the perpendicular distance, is this one here. So if I do that distance, there's no right angle there. It's not perpendicular at all. In this one, it does happen to go through the thing that's turning, but that is not always true. So you have to remember that you need to have a right angle between the distance that you're measuring that goes from the turning point or the pivot point to the line of action of the force. And the line of action of the force doesn't have to be buried inside the object. Okay? Right, so in your data book, you're probably going to find that it says that moments are equal to FD, so force times distance. The units of these, have a little think for yourself before I give you the answer. The unit should be Newton meter, because it's force times distance. Unit of force is newtons, unit of distance is meters, so squash them together, Newton meters. And again, these have a direction, so they can either be clockwise or anti-clockwise, and that matters. You need to think about which way the force is, which direction the turning effect will be, because it's going to matter. Okay, so if we have a look here, force F is exerting an anti-clockwise moment on the through the spanner onto the nut. Okay, so the moment of a force, therefore, is going to just depend on two things. It's going to depend on the size of the force, so bigger force, bigger moment, and it's going to depend on the distance. Bigger distance, bigger moment. I'm going to show you some examples in class that illustrate that beautifully. It's really, really easy. In fact, I may show you a video of someone trying to swing a very large sword to make my point. Okay, moving on though, this brings us to a very important principle, and this is the principle of moments. What this says is that when an object is in equilibrium, so when it's balanced, the sum of the anti-clockwise moments is equal to the sum of the clockwise moments around the pivot, around any point, sorry, to be clear. So I can take moments about any point. Now, with this thing, it makes sense to make it around the pivot point. It's nice and easy and it's simple. There are times when I might not have a clear pivot point, but I can use the principle of moments to make any point a pivot point. But principle of moments. An object is in equilibrium when the sum of the anti-clockwise moments equals the sum of the clockwise moments. So what we can say is that if the ruler above is in equilibrium, then W1 times D1, so the anti-clockwise moment, has to be equal to W2 times D2, the clockwise moment. So principle of moments is going to be very, very, very useful to us. Okay, so as well as moments, we also have something that's similar and related but different, which are couples and torque. So a couple is a pair of equal and opposite forces that act on a body but not along the same line. By the not along the same line bit, basically I mean that the two forces are separated by distance. So it's not like I've got F up here and F down here. That would be along the same line. These are separated. So if we just have a look at what I've got in the picture, sorry. If I look for the total moment, now this F is going to be making it turn clockwise, and this F is also going to be making it turn clockwise. So they're both clockwise moments. So if I add them together, I can find the total clockwise moment. So the moment caused by this one is going to be F times X, because it's pivoting around this point. And the total moment by this one is going to be F times D, so the total distance between them, minus X. So basically, if I've got X and D minus X, then that gives me D. So the total moment of these two things is going to be equal to the force, well, the size of one of the forces, times by D, which is the distance between them. And this is a very useful thing about couples. So for a couple, it doesn't matter if they're pivoting around a point that's equally placed between them or not, the size of the moment they cause, or their torque, is always going to be the size of one of those forces multiplied by the distance between the two forces. So if I have a couple, two equal but opposite forces that are causing a turning effect that's separated by a distance, the size of the turning effect that they cause is equal to the force, the magnitude of one of the forces, multiplied by the distance between the two forces. And that effect we call the torque. So if a couple causes a turning effect, that turning effect is called torque. So just some things about a couple. The two forces in a couple, they've got to be equal in magnitude. They should be parallel but pointing in opposite directions, and they have to be separated by distance d, because if they're not separated by distance d, then they're not going to cause any effect. And just to be clear, the definition of the torque of a couple is that it's one of the forces times the perpendicular distance between the forces. And finally, why am I bothering to tell you all this? Because it's useful, is the answer. Basically, we can check to figure out if something's going to balance or if it's going to rotate. We could either calculate an unknown force or a distance if we already know that the object in question is balanced. So I am just going to show you an example. So here I've got a seesaw. I've got a 20 Newton weight on one side and a 40 Newton weight on the other. The 20 Newton one is 2 meters from the pivot and the 40 Newtons is 1 meter from the pivot. And the question is it balanced? Will it remain in equilibrium or will it turn? Well, we can figure it out. And this is another one where thinking about how you're going to lay it out always helps. So I always try and think about either, with this situation, anything that's on the left-hand side is going to cause an anti-clockwise moment, and anything on the right-hand side is going to cause a clockwise moment. So I'm just going to split it left side, right side. But sometimes you might want to think anti-clockwise moments, clockwise moments. But as I said, we'll just pick left side, right side here. So to calculate the moment on the left-hand side, that's going to be F times D, so 20 newtons times 2 meters, which gives me 40 Newton meters anti-clockwise. I then look at the right-hand side. Again, at the moment is equal to the force times distance. So force is 40, distance is 1, 40 by 1, which equals 40 Newton meters clockwise. So my anti-clockwise equals my clockwise, so it's balanced. Easy peasy. Now, if I didn't know one of these, I could calculate, but I knew it was balanced, sorry. So if I didn't know the 40 newtons, I knew the other two distances and the weight over here, and I knew it was balanced, I could figure out what's going on the left-hand side, and then just use a bit of algebra to work my way back to find the thing I didn't know, so the 40, say. So, all quite useful. We'll look at some more complicated examples in class, don't you worry. But I think it's quite nice. There's a nice logic to these ones. So remember, any questions, ask me when you see me in class.